Today is our Tuesday, February 20th meeting. Good, all right. Everybody got a newsletter, I hope. I didn't see the email bounces. And I got a message about the survey. I just put it in on page 2 and I had a link. So I ended up sending an email out just for that with a link in it. So I did the email and a couple other people did the survey. Appreciate it if everybody can do it. And that includes new members, old members, all the members. We're not looking for personal information or anything like that, you know. We're not going to sell anything except for you. I'll tell you the time.
Won't get much.
Hey, a couple of yen is good. I forgot what they call it.
Yeah.
And so there a lot of work went in by Ben and a few other people to come up with a decent survey. And it's not very long, takes a few minutes, ask good questions about interest and some other things, nothing real hard. And there's even some places on some of them where you can click other and fill in something else that you want or interested in. And this data would help us kind of steer the club in terms of speakers or programs or other things, so we can maybe make the club a little more lively and get a few more members to show up, which we need to do out there. So, and we're waiting on our speaker for 9. He said he'll be here a little after 8. So did,
getting away.
oh, he's on his way.
So he's gonna be around here.
Okay, our speaker will be around 8 o'clock. We got about 10 minutes. Did anybody have anything they want to talk about or anything they've done?
Yeah, just mention, there's a new book out,
Step up here.
brand speaking, called Totality,
Come this way. Not, there you go.
the Great Eclipse, whatever like that. Published this year, so 2024. It's chock full of everything you ever wanted to know, dream about, or everything about eclipses and everything, 300 some pages. And I got this at Barnes and Noble at Glenbrook. They have about 3 or 4 more copies left there. When I got it a week ago. And it also gives you a highlight, you know, all the science, everything about it. If you want to go, it also projects for the next 10 years, whatever like that, all the eclipses around the world are like that. Shows the past, shows the map, shows everything, and includes all the sites. It's a great book, so I highly recommend it. But Totality, the Great North American Eclipse of 2024. Reviews of 2017 eclipse and everything too. Only 95, so that's a sales. Well, you might get it, yeah, look it up on Amazon, Mark Littman and Fred Espinac. And like I say, Barnes and Noble and Glenbrook have 3 or 4 copies there, so every once in a while I walk over their little science section and see if anything new. And there's usually not, and the fitness section just keeps getting thinner and thinner. But anyways, they had these up there, and it's pretty good. You know. So one other thing Saturday, I was over to Lyman, Ohio, to meet a couple of friends, and I was there early, so had some time to go. I went to the Lyman Mall. I ran into the guy who's now the treasurer of the club over there, but he used to be the president. You know, the head for Michael Ritchie was a guy named there, and he said he used to be a member here years ago. And so, anyways, I got some details from him and everything. They got back their scope that was stolen August of the year ago, but it was all toward to hell. So they got one of the culprits or whatever like that. Luckily, Lyman's got a prison up on the north side of town there, so they don't have to drive too far. And so anyways, they ripped it off and they kind of tore up the scope, messed up the screws, they took it apart, they run a paint it, they put it back together, but then they screwed up. They didn't take the equatorium out, but they screwed that up. And so they stripped the gears or whatever on that. So, but anyway, it's going to be felony charges against the. So anyways, they got ambitious. This guy, he filled out a foundation for a grant for the state of Ohio, and they awarded him $250,000.
Wow.
And now the observatory was done, I think in 1964, the city park in Lima. Lima is only 40,000 people, so it's not a huge town. But anyways, so they're going to redo it. They didn't have air conditioning before. It's going to put in an HVAC system. They're doing some painting. They're going to increase their parking lot where they cut down a couple, you know. They got $250,000 from the state of Ohio, and they got another $30,000 for the local park thing, they call it the Johnny Appleseed, park, Metro Park System, one like that. So they got $280,000 total. So it ought to buy a few things, but he says, well, I don't think it's gonna get us a scope there. Apparently, you get government grants, you know, a lot of hogs in that trough. So by the time everybody starts, dipping from that trough there, probably won't take too long for $250,000, $280,000 this period. So he's talking about, writing another grant for $200,000, that he wants to try to get a plane wave 20-inch scope. Now, this is in a light dome in downtown. But anyways, that's their plans, whatever like that. So, interesting talk, just had to show the right time.
How big was the scope that was damaged?
The largest Celestron is 14-inch Celestron with their thing.
Did you get a copy of one of his grant writings so we can kind of?
Learn, I don't know.
If he's so good at it, he's the guy to talk
You
to.
gotta get to the government facilities there, like I said, I'm in the state of Ohio grant, now it goes through like the city owns the observatory, so it goes through them. Key holders have to go to the city of Lima and sign out their keys at the city desk.
Every time.
No, not every time. They don't have track of who's a key holder, so it comes with strings, it looks like it. I just thought I'd mention it there, but, I was pretty impressed. And so for the eclipse order, they bought 5,000 pairs of glasses. So if we run short and you need something on the last minute, 5,000. So, and they had a price on there at the $4 each or 3 for 10. So that's what they're selling for.
5,000.
Yeah.
I think they're probably gonna have some leftovers.
For one time for that. Now, it wouldn't surprise me if they go down to.
Eclipse for a while, so they got stuck within the extras.
Well, they passed out someone to the retailers around Lima, some different stores or whatever, who were graciously selling glasses for them and giving some money or whatever like that, so. So they're doing that, and they're kind of located close to Wapakoneta, so they might have a table or something down there at the Armstrong Museum or something during the day or something there too. But
I've never been to that museum. I need to go. Just for
if you're going to 33, it's a good place to stop off for an hour or so. Anyway, that's like, but I recommend this book if you're.
I'll take a picture of that cover in a little while.
Because, I mean, it's got all the science and all the historical stuff too, and it's not just about the 2024.
Well, that was great. Good info. Anybody else have any? Step on through. Don't do our crime. Step in the projector.
Only a few numbers.
All right, when you looked at your newsletter, you saw that there isn't any observatory training scheduled. Mainly because focusing on preparation for the April 8th eclipse. If there's anybody that is really excited and wants to be trained, we will fit them in. They'll just need to contact me and we'll get things scheduled. So, or if you hear of somebody that is interested. I would like to ask those that are not planning on traveling out of the area on April 8th for the eclipse to be able to help out at the observatory. At this point, after listening to Homeland Security's report to Little Old Wells County, we're sunk because we have a larger population draw. They're talking that Wells County could increase in population from 50 to 50,000, and that is a county of about 28,000 people. So roads clogged, internet not working, cell phones not working. So we need people to help out at Jefferson Township Park to help with parking, crowd control. If there's anybody that's a nurse or will probably be good to have a first aid station just in case. We'll probably need to provide or have a limited amount of refreshments. And that all of this is in addition to doing the live cast from the observatory, hoping our internet doesn't go out, and also working with the public. Adrian's already volunteered her robotic scope, in addition to us using the 12-inch Crow harnish figure scope. So contact me, and as we go through March, We are going to have a number of programs. We're just starting to get everything filled in. It'll be a very busy and exciting month and a great opportunity, and apologize for being on the late side. Laura, Russell and I were out at the observatory. 21 did 2 interviews, one for just a brief blurb about the observatory and then one talking about the eclipse. And I expect that we'll probably be doing likewise with Wayne 15 soon. If you are interested in helping out with something like that, give me an email, a phone call, because the more people, the more variety of faces, the better the media presentation. And I want to thank Phil for his work on the wonderful poster for the eclipse, and then also reviving the how to view the eclipse handout. So that'll be very much a part of our communication. So, Russell, can you get that? Russell. Wrong way. We're working with a robotic camera for this evening.
Oh.
Hopefully this is working out well for those that are online. Let us know how the audio is and also how the video is. So, thank you. Oh, question in the back.
You on this, channel 21 is gonna broadcast what you.
They were going to do the short blurb at 7, but we're not sure it actually went out. And we don't have an actual date. Lot of conversations and questions. They'll be editing down to whatever their piece is. So, all right, yes.
The other day I was out by the observatory, there's a bunch of those blue flags run halfway along
And a
there.
no parking sign.
Yeah. You know who put those up?
I'm guessing that with the stands put up by the tractor pull area, that whether for horses or tractors, they must have had a large event out there. Or are planning on having a large
Yep.
event.
But I thought maybe they're gonna bring in some stone or something like that. The flags are only in front of our place, about 3 foot from the road into the berm. And then there's one sign where you normally pull up along the fence on our side that says no parking, nothing on the other side. So it kind of raised a question if anybody knows anything's going on. That was my only thought, was that maybe since they put in that ball diamond, they're gonna dump a couple loads of stone in there, because there was originally a stone dumped there. There is originally a little drive underneath it.
Being on that road there.
Yeah, that was
On
not
the
full of
fence?
grass. Yeah, along the fence line, there's stones, at least 50 foot or so.
Very good. Well, that's it. You'll be here soon, it's a minute after. Anybody else got any observing reports or any neat things they've done with astronomy?
I think Dwarf Telescope.
You wanna talk about real quick, cause our speaker.
Yeah, we'll do this real quick.
Go ahead, do it real quick.
This is the Dwarf, it's a low light, 24 millimeter objective, it's probably the smallest telescope on the market. It's automatically go to, it takes pictures of the sky, figures out where it is. It'll be on your target in probably less than 30 seconds. And it stacks automatically, so you see the image building as it goes along. Which has thing to do post processing. The battery, it's got a battery operated, or you can plug it into the assist if you're shooting a long time. Battery lasts about 2 hours in 16-degree weather. And but it's I got some pictures taken with it. If you want to see it a little later and see me, and it's amazing. So that's it. This is what it comes in. It's got a tripod. It's a little tabletop tripod, and
So that tripod didn't come with it. So.
no. And by the way, this tripod is it's in equatorial mode. So this is 41 degrees, and I set it up, and then I get less hydro. So that's pretty cool. So it runs around $500. Like I say, you can have it parked in your deck and be up and running in probably within a minute and connected, and it's pretty cool. So anybody, I got 5 telescopes for sale.
All right, our speaker just arrived. We're gonna listen about galaxy formations evolution. This is Dr. Ryan Farber, excuse me. He sent a little bio, and after growing up in wine and cow country in California, he graduated from Wheaton College with a bachelor's degree in physics, mathematics, and minor astronomy. During my undergraduate years, I engaged in various research projects, including search for transient lunar phenomena, determining the circulation time for material in Europe's ice ocean, and simulating cosmic rays propagating through the turbulent magnetic interstellar medium. That's about cool. Thereafter, he attended the University of Michigan for a PhD in astronomy and astrophysics, studying why certain galaxies stop making stars. After that, he worked on Max Planck's Institute, is that right?
Yep, Max Planck.
Max Planck Institute for Astrophysics in Munich, Germany, as a postdoctorate researcher studying the galactic barren cycle, which I'm sure you'll tell us about that. He's currently visiting assistant professor in physics at Purdue University, and he just came across the way. Teaching introductory courses in physics and astronomy. So when you're ready, we'll turn it over to you.
All right, so I guess I'll just start while my Zoom is updating by mentioning that this is not, unfortunately, going to be a research talk. I mentioned to Mike that I could give a research talk, but not under shortish notice. Instead, this is going to be sort of a combination of material that was from my Stars and Galaxies class that I taught last semester. And so a lot of this is maybe material that you've heard of before or know of before. Hopefully some of it will be new or presented in a bit of a different way. But the other thing that I'll mention while this is, I think, still launching, is that because this is from my classes, you're not going to be able to just sit down there and be quiet. I'm going to ask you all to participate at a couple different points. And this will be much, much more fun if you do participate. So I'm calling this, again, kind of class number 1, if you will, because this is borrowed from course material. Does anyone know what is shown in this image? It's a little bit low resolution. I see the Milky Way. All right. So this was actually taken somewhere in Indiana, though. Sagittarius at the bottom. Probably have Sagittarius down there. Yeah, we're looking kind of towards some big fluffy part of the Milky Way. So this was taken up at Tippecanoe State Park. So if you have a better picture of the Milky Way than this in the state of Indiana, I'd love to use it in my future courses. This is the only one that I could really find, and it's not super high resolution. So if we switch locations over to Fort Wayne, and then this is at 10 o'clock tonight, we have a couple of stars labeled up there. We have Polaris, and then I don't know how to say these. Maybe some of you can help me. Dookie and Alif or something like that.
Like in the you know.
Okay.
Yeah.
Dookie. All right.
Frank's enough.
And then Alia.
I think the upper one is normally pronounced W, but I've
Okay.
heard different pronunciations. It's kind of like Beetlejuice. Everybody has a different pronunciation. So.
Okay, sure. All right. So given that we have some of those stars titled, do we know what constellations or kind of where in the sky these things are?
Polaris is to the north.
All right, so I heard that Polaris is towards the north, so we must be looking kind of generally towards the north. So maybe I'll add in some constellation lines, and that'll help out a little bit. I don't think that you all can see those very well. It's very faint. So let me add in constellation labels. We have Ursa Major over here. And then we have Ursa Minor with the Little Dipper, probably that you all were noticing. And then the region that this is centered on, though, is kind of right in between Ursa Major and Ursa Minor. And if we zoom in, this is currently showing a field of view of 42.6 degrees. So a huge patch of the sky. But if we zoom in, I don't actually see anything there anymore. This is zoomed in to where we're showing 0.00139 degrees, or in other words, a little bit more than a few arc seconds. So a very small field of view. Now, why would we care about a region that is totally devoid of stars?
Hubble Deep Field.
Hubble Deep Field, all right. So this is where the original Hubble Deep Field was looking, was kind of in this region between Ursa Major and Ursa Minor, where there are extremely few number of stars. So this was taken over the course of Hubble staring for 10 days back in 1995. And I want all of you to, you're already kind of in tables of groups of 2 or 3. Put on your pure observer hat. I'm more of a theorist. And your goal will be to try to be as little of a theorist as possible. Chat with your neighbor. Just looking at the colors or other distribution of light, you could say, what do you see in this photo? Try to be as observer experimentalist as you can. So go and chat with your neighbors for a minute or two, and then I will call on some people.
They are identified that they're all galaxies, some further away.
They look just like any other galaxy.
Some are farther and some are closer.
Further away.
Yeah, when the Vegas, but we have to be bigger.
Don't they look like normal galaxies?
Compared to other parts of the sky.
About every possible position of the galaxy.
Okay, so I think that that's enough of a time for y'all to chatter. I ask the gentleman in the green plaid shirt, what did you observe?
I was saying, it's, they tell us it's all galaxies.
Well, they tell us, but what do you see?
I see, well, they're different colors, some,
Okay,
right?
see some different colors, yeah.
Tending toward the red, and I would presume the redder they are, the further away they are.
Okay,
Possibly.
okay, so maybe redder means farther.
Things wrong.
All right, yep, thank you. Can I see maybe a show of hands if anyone else wants to contribute before I pick on someone else? Yeah.
The galaxies look very familiar. It's almost like the coma region. So the galaxies that are far away are looking a lot like galaxies that are close.
Okay, how do you know these are galaxies?
You said they were.
I said.
I don't remember saying that.
But I have been told about.
Maybe I mentioned that, but what I guess should have said or meant to say is this is the Hubble Deep Field. I think that I did mention, like, okay.
They have angular dimension though.
Okay.
It makes you think that they're galaxies.
Okay, so thank you. So whereas for stars, even with the telescope, we just see pinpoints of light. With these objects, you can see that there is some smearing of the light. Okay, and we heard that there were colors as well. Now, are they all just smeared as kind of circles or spheres, or do they all look the same?
No,
No?
there's some that have, different shapes, and you do see a little structure in some of them.
Okay, so you can maybe even see some substructure. Down here, I can see a little tiny kind of wispy or spiral like pattern. It seems like. All right, so this was the original Hubble Deep Field back from 1995. Now, Hubble has been staring at this deep field a number of times since then. And in a sum total of all the deep fields ever taken, we have now what's called the Hubble Extreme Deep Field. Yeah, and this is unfortunately, I think, rotated a little bit or so compared to the last image. So I don't recommend trying to find exactly one galaxy here compared to the galaxy in the original Hubble Deep Field. But so I want you all now to think along similar lines, I'm a theorist, so sometimes I will toss out theories like, oh, I see a bunch of galaxies here. Try to put on your pure observer hats again and think a little bit more about what this image tells us and what this image could tell us compared to the previous image that we had. So go ahead and chat with people for another 30 seconds or so, and then I'm gonna pick on you.
Yeah, that'll be a little picture up in the corner. He's got a flip flop, but this is the main screen, and then this will be a little picture in the corner. I must have it.
But it's like.
The rudders are red.
Yeah. And let me put a lot, and one portion, I think, something associated with, gravitational laser. Distortion. I don't see that in this one. Yes, I'm not sure.
Okay. Wrap up your conversations. All right, now. Adam in the blue or so, or who, could you mention what you observed?
What we could tell from back here is that there were definitely more objects in this image than there were in the first one.
Okay, so more objects, all right, and then in the gray hat.
Yeah, more objects, that's.
Did you notice anything else?
More colors?
There are more colors,
Yes.
Okay.
so.
A lot more, yeah, just a lot more stuff, more colors.
More colors, so are the colors, if we were saying that before, we had some that were, kind of more red, some that were more white and blue. Is it just that do we have greens and purples and just totally different colors now, or are they somewhat different shades, would you say?
That's red.
Yeah. They're red, maybe different shades of red, maybe different shades of blue. Now, I didn't actually notice, I think, any stars in the original Hubble Deep Field. Maybe there were some in this kind of quadrant that got chunked out or so. Does anyone see any stars in the extreme deep field?
They have spikes on it because they bubble.
All right, so I heard something about spikes, and
I don't see any, but.
Yeah, there's one right there.
okay, so maybe there are a lot of objects here, so that's fair. I see one up here. That could be disguised as a galaxy, if you will, but I see some pretty noticeable spikes. Someone else see another one?
Right.
Okay, so there's another one right here. I'm not sure if there are any more. One of the problems with trying to understand what is in this image is even in a region that's relatively devoid of stars, you almost always intercept some faint stars that you didn't even know existed until you decided to look at that region of the Milky Way, or accidentally look at that region of the Milky Way. All right, but Hubble is not the flagship space telescope anymore. We now have the James Webb Space Telescope, and so this is an image that maybe you all have already seen. This is called the James Webb First Deep Field. But this is a little bit different. This is not actually pointing towards that same patch of sky. This is now looking at a galaxy cluster. SMACS 4730, it's towards Virgo. It's in the area of the sky of the Virgo constellation. This is a galaxy cluster we think about 4.5 billion years ago. So when the solar system and Earth was forming from the molten ashes left over from the formation of the sun, when the really first rocks were forming on Earth, this light began its journey towards us. And now this is the James Webb Deep Field. What's the difference between James Webb and Hubble?
Infrared.
Infrared. This was taken with the NIRCam camera. So there are a couple of different wave bands which are being, so this is not kind of a natural light image. What looks blue to us right now in this image is not what would look blue to our naked eye anymore. Instead, this is a combination of different wave bands. But what you might be able to notice is that there are a lot more galaxies, a lot more small smudges that are red or orange in this image compared to the last one. And I can put them side by side. And there's another glaring difference, I would say, between the Hubble Extreme Deep Field and the James Webb Deep Field, or first deep field.
Resolution.
So resolution, yeah, I mean, so there's a lot more clear in James Webb. That's a good one. I wasn't thinking of that actually. There's a couple of big differences actually.
Well, because I see what could be like a gravitational lens and effect.
All right, so yeah, keep in mind that this is looking towards a galaxy cluster. This was meant to be a region pretty devoid of stars or known galaxies for that matter. So the light coming from us here is traveling about 13 billion light years from very shortly after the Big Bang. Here, most of it, 4.5 billion light years that light is traveling. But there are some of these arc-like features that maybe some of you noticed. Those arcs, we think, are gravitational lensing done by the galaxy cluster. So these are background galaxies that are being warped and also magnified. So part of the reason why James Webb decided to stare at a galaxy cluster instead of the same empty or relatively empty field that Hubble did is that because of the magnification effect from lensing, we get a much higher resolution to study these background galaxies who are from some of the first moments after the Big Bang, or first million moments, if you will. The other thing that I really noticed is that there are a couple of huge obvious stars in here. Whereas there are still two or a few in the Hubble Extreme Deep Field, but I thought a little bit harder to notice. Okay, so switching over to kind of more of the lecture, and something that probably you all know, there are a couple of different galaxy types. I think that we identified that there were not just all round, blobby objects that we were looking at before, but there were some that had some structure to them. Some of those looked relatively edge on or like a pancake on its side. And some of them we could see more of these spiral patterns. And there are also some galaxies that are intermediate between the two. And here we have a very prominent galaxy with a very nice bulge. Has anyone observed this galaxy before? Yeah. Okay. Sombrero galaxy, yeah. All right. And then how about for this very nice barred spiral? I actually don't know what this one is, so I'm curious if any of you recognize it, but I don't know which one.
Oh, yeah, we know that.
All right. And so we noticed that there are not just these different types of galaxies, but even with the spirals, there are different properties. Some have a very prominent bulge of stars, some have a elongated structure rather than that spherical structure. Now, question that I want to ask you all to think about for a few moments. We were talking about how there are different colors. These ones have bluish or blue-white colors, these spiral galaxies largely do. And some theorists think that this means that there's ongoing star formation. I want you all to think about why that might be. And there are a couple of multiple choice options up there, but you don't have to feel constrained by what I was giving my students. So feel free to chat with each other, give it a thought.
What's the question again?
So the question is, if there is ongoing star formation, why does that mean that there's this blue-white color? Or to phrase it differently, why would a blue-white color mean that there's star formation?
It has to do with heat.
So the
newer stars. Probably the temperature.
Stars are extremely hot, extremely bright.
Okay, I think that you all chatted about it long enough. Let me go to the gentleman with the crossed arms.
I believe the last one where it scatters, yes, it's scattered by a blue light, and you can't really tell what's going on.
Okay, why is the sky blue? Has anyone heard of this before? Sky is blue because there's scattering of the light, and blue scatters more than red. So we typically have blue scattering towards our eyes. Anyone think about the other options up there about there being just a deficit of red or yellow stars that could explain this?
Yeah, I like the.
You like B?
I don't know about a deficit, but blue stars tend to be really big and really hot.
Okay,
So they're really bright.
so blue
They
stars.
might dominate the light without necessarily dominating number.
Okay, so even if there are only a few blue stars, they could still shine or outshine the red and yellow. So that's, and it's a fair point to think about the scattering. And we actually do think now that there are some extremely dusty galaxies that Hubble didn't really notice because there was not enough visible light coming through. Keep in mind that with James Webb, though, we're not actually looking at really blue, intrinsically blue light anymore. We're able to see through the dust. And so the reason why we get this blue-white appearance is related to how massive stars, it's not just that they have a brighter luminosity in general or have a brighter shine to them, but because they are hotter, they emit more UV, blue, green, red photons, etc. So even when you're looking at an infrared image, the stars will look bluer in that infrared image if they're the massive stars compared to the stars that look redder. So they're bluer or they're brighter, not just in the blue, but in all wavelengths. Okay, and then for this next question, we're going to consider if galaxies take billions of years. Has anyone been observing here for billions of years? I don't think so. We're all a little bit too young for that. Galaxies have been supposedly changing over millions, billions of years. How do we actually know that they change? Yeah.
Well, I mean, my understanding is that they can run an HR diagram of stuff and. You know, that's your period, that's your luminosity and temperature, right? So the short-lived stars that are kind of bright, they look at different clusters, for example, some of the clusters are old, and the whole diagram's truncated. But the other answer is that it's a little bit like going out to a forest, that there's lots of trees. And, you know, you don't see the redwoods growing, which is great, but you kind of figure the saplings are gonna turn into bigger trees.
Yeah, so that's the fun part is the botanists actually have the same problem that the galaxy theorists have. The botanists cannot wait 1,000 years to see what happens to the redwood trees. Or tens of thousands of years for that matter. Instead, they have to come up with some sort of model and try to understand based on what the population looks like. If they can notice changes within the population, which suggests how individual galaxies might change over time. So we have not just spiral galaxies, but in our population, we have what are called lenticular galaxies. They definitely still have that flying saucer shape to them, or that elongated shape to them. But they look much more fuzzy, if you will, compared to a regular spiral galaxy. And then we also have some big elliptical galaxies. Does anyone remember why M87 was a big deal a couple years ago?
Black hole.
Black hole, yep. So this was where we first were able to image the event horizon of the supermassive black hole. The M87 has its supermassive black hole of around 1 billion solar masses. But in any case, we find that for the red, yellow colors, we were looking back at the Hubble Deep Field, those objects tend to be rounder. And then if we compare to some other galaxies that are much closer by, this is the Large Magellanic Cloud, has really no sort of similarity, I would say, to the spirals or the ellipticals. This is what we call an irregular galaxy, which do not really otherwise neatly fit into the trends, but are nevertheless very interesting. And so what Hubble did about 100 years ago, 80 or 90 years ago now, is he looked at all the different galaxies, and he thought that the ellipticals were sort of the beginnings of galaxies. When a galaxy was born, it started out nice and circular, and then depending on how it had collisions with other galaxies, it might end up with some more prominent bar, depending on if those galaxies fall close to one of their rotation axes, or if they missed each other, they ended up as spiral galaxies, with a not as prominent bar, but a more prominent bulge. Now, it turns out that modern theory suggests that we have galaxy formation happen the other way around. Instead, we start out with a nice long spiral shape, and after those spirals merge together, they will typically merge at random orientations and end up with a larger and larger assortment of spherically orbiting stars. All right. And then if we take a look, so this is kind of like the HR diagram, but this is the galaxy HR diagram. Unfortunately for the HR diagram, we can really only resolve star clusters in the nearest galaxies. So most of the galaxies that Hubble or James Webb sees in those fields, we cannot come up with an individual HR diagram for those stars. And so each one of the points on here is a different galaxy based on how bright it is, luminosity on the y-axis, and then the color on the x-axis. And so what I want you all to consider is how does this suggest what I was talking about earlier, which forms first, the blue spiral galaxies or the red elliptical galaxies? So maybe chat with your neighbor for a moment and then we'll come back to that. Yeah, so I don't just want to answer, but I want you to try to come up with the explanation too.
It could also indicate being older as well in relationship to us, the distance.
Well, it means the times. Because it'd be the farthest way, so I've said it, right?
Alright, okay, so gentleman with the hat in the front row.
So are the red galaxies further away, greater redshift?
So, alright, so red galaxies, maybe farther away with a higher redshift. It turns out that if we take a complete sample and we restrict ourselves just to short redshifts, and by small or short or small redshifts, I mean less than 0.02, so this is going out to Virgo or a little bit beyond Virgo, maybe out to the Coma cluster, and we're just counting up all the galaxies, then we don't think that there's a significant shifting of the light in that case, but we still end up with something similar to this. Yeah.
Spiral should be blue and elliptical should be toward the red side.
All right.
It's going to last.
All right. Spiral is blue, elliptical is red. I also saw hands.
The younger ones are blue,
All right. Why?
the older ones blue.
Why are the younger ones blue?
The thing is that, there's not as much, star production in, new stars in the redder galaxies to the left, or to the right.
Okay.
And so it would make me think that they are older.
Okay, so that is one thing. These objects on the right are redder. We've talked before about how when you have a star cluster, the blue stars are the more massive ones. They live fast and die young, so they disappear. And then we're just left over with the red stars. So if we're seeing a red object that suggests that it's older, there's another piece of evidence here that's suggestive. What are the brightest galaxies in this image? Well, okay, quasars, but how about in terms of red and blue, which ones are the brightest according to this graph? Looks like the red ones, which is a little bit surprising because we talked earlier about how the blue stars tend to outshine the red stars, even if there are relatively few blue stars. So that is suggesting that there are a really incredibly large number of additional stars in these elliptical galaxies compared to our spiral galaxies. And unless these galaxies are losing stars over time, which we don't really imagine happens, instead we think that galaxies largely increase the number of stars that they have with time. That also suggests that we end up forming spiral galaxies first and ellipticals later. Hubble didn't have something nice like this. This is the reason why we think that Hubble had it backwards. All right. And now in terms of where we find galaxies, we often find spiral galaxies in what are called groups, where there are a few to a dozen other galaxies there. Has anyone heard of the local group before? Okay. What is your favorite object in the local group? Let's go with the white shirt. Andromeda, okay. Any other objects in the local group aside from Andromeda? So there are the Magellanic Clouds. There are a bunch of little dwarf galaxies. We're learning about more and more of them. The only other major galaxy aside from the Milky Way, though, is Andromeda in the local group. Now, in contrast, elliptical galaxies tend to congregate in huge packs. So this is the, I believe that this one is Coma cluster. And so each one of these orange-red objects we now know is a galaxy. And I see hardly any blue in this image. This is a star, doesn't count. There are a couple of blue galaxies here. But in comparison to the group that we looked at before, there are hardly any blue galaxies here. Any thoughts as to what happens to them, or why aren't we seeing them?
Took a lot of time to create that big of clump.
Okay, so maybe it just took a long time to form this clump, and therefore all the blue galaxies have kind of died off or so. Any other thoughts about where the blue galaxies might have gone off to?
They're converting to red,
Maybe we had blue galaxies and they got converted to red?
yeah, they're aging, maybe they're aging.
Okay, so it sounds similar. Why are they aging? Did it just take a long time? Or are they aging faster?
Oh, because the blue stars die off quicker than the wandering red stars.
Yeah, so this is still to some extent an open question, actually, as far as why the galactic environment impacts how many blue galaxies and how many red galaxies we see. Best models for galaxy formation from quantum fluctuations after the Big Bang evolved for billions of years suggest that we actually formed galaxy clusters earlier than we did the spiral galaxies like our own Milky Way. And that there are still spiral galaxies that will eventually fall on to these galaxy clusters. Whereas the Milky Way and Andromeda will collide in just a couple of billion years, we think that the Milky Way Andromeda merged system will eventually fall onto the Virgo cluster in around 100 billion years or so, if the expansion of the universe doesn't rip us apart before then. But that's a little bit of an open question. What exactly will happen there? And so there are a couple of blue galaxies. They tend to be farther from the center of this image. I see a couple more, but they're all pretty small and hard to see. So the idea is that these blue galaxies get converted pretty rapidly. And one of my research projects during my PhD was studying this. And it's a similar effect to how when a dog sticks its head out of a car, what happens? And maybe its tongue starts flopping back or so. So that is due to an effect we call ram pressure, or the kind of wind force, if you will. Galaxies that fall into a galaxy cluster, there is a hot intra-cluster medium of material that they ram into. And although space is extremely tenuous, galaxy clusters have a bit of a denser environment than what we find between the Milky Way and Andromeda. And we think that that could be one of the reasons why we don't notice many blue galaxies except for at the very outskirts, is that their star-forming fuel gets stripped away. All right, so the environment seems to really matter. And so we've talked so far about how there are a couple of different types of galaxies. We didn't really talk about gas and dust too much, but one has found using different wavelength detectors that there are a lot more gas and dust in the spiral and irregular galaxies compared to the ellipticals. Now, one thing before I keep going all the way, when Mike invited me, I actually hadn't thought about this until this morning, but I have a student who's doing research with me right now. And what he wants to do is redo the Eddington experiment, because we have a total solar eclipse of the sun coming up quite soon. I'm sure you're all aware of that. And so he's currently learning general relativity. He doesn't have a telescope of his own. We have some 10-inch Dobsonians in the department that he was going to borrow. But he is seeming a little bit overwhelmed with the theoretical part of this. So I'm curious if anyone happens to have images of Pisces that they have taken before. Unfortunately, this is not a place where I'd really expect anyone to have taken an image, because it's a relatively uninteresting place. There are not a lot of nebulae, not a lot of bright stars there. The other thing is that if anyone's willing to help this research student take an image there, then I'm all ears for that. Mike, how much more time do we have? We're kind of in between part 1 and part 2, but I wasn't sure how much to talk for.
20 minutes, would that be?
Yep, okay, sure. I should be able to wrap up part 2 in that time. All right, so moving on. So this next part, we're going to talk about a little bit more detail about why we know that all those smudges are actually galaxies, rather than just some comets or other comets that are passing through our solar system, or some star clusters in our own galaxy. This was the so-called Great Debate in the 1920s. The American Association for the Advancement of Science had two great astronomers present either side of the argument. Has anyone heard of the Great Debate before? Okay, so this was a huge historical thing. And Hubble was the one that really showed that we had these objects not just inside of our Milky Way, but external galaxies. And then we'll talk about how building up this distance ladder to measure how far these things were away led us to the Big Bang Theory and the origin, this idea that the universe had a beginning. Okay, so for how we measure the distance to galaxies first, we have to use an array of different methods. And this comes down to what's called the inverse square law. I can see, show of hands, people know about the inverse square law. Maybe some people don't. Some people, yes, some people know. Okay. So the idea is that when we have any sort of light source, like this projector, for example, if I cover up the light very close to it, we end up with a very large dimming. If I move a little bit farther away and I move my hand, how much less dim would you say it is now? How much brighter? Maybe 20%. Okay. And if I move my hand maybe half the distance, how much would you say now? 40. Yeah, 40. That's 40? Maybe. Okay. Let's try going one more time.
90%.
Maybe 90%. Okay. So the idea, and this was a rough experiment, the idea is that the amount of brightness that you should be blocking should be squaring. So we shouldn't have gone straight from 20 to 40% exactly. So I think that that'd just be a linear increase. Or the other way of putting this is that the farther away from a light source something is, the dimmer it should look. And it's not just a linear dimming, but a dimming that goes as the distance squared, because we're thinking about spheres. And so we can use this, but first we're going to figure out just the size of our own solar system. And these days we use radar to do this. Does anyone know how we first found out about the size of the distance from the Earth to the sun? So it's actually predating radar. Yeah.
Yeah, they had the expedition to observe the passage of Venus across the sun.
Yeah, so the transit of Venus, which there's a play about this now. There were a couple of different folks that tried to view the transits of Venus, and a lot of them had a whole lot of bad luck between different wars, between cloudy nights. One person waited 12 years at an island. It was ordered by a sponsor to switch to a different island for the observation. And there was just one little cloud that covered up the sun during it. But we eventually got to figure out the distance from the Earth to the sun using transits of Venus. These days we use radar within our solar system. Going out a little bit farther, we can notice when Earth moves around the sun that the very nearest stars to us appear to shift their positions. Parallax. All right. And if you haven't heard of parallax before, or maybe even if you have, the way you can more obviously understand how this works, if you put your pinky up pretty close to your face and you blink your eyes left and right, you should notice that there's a shift or a apparent shift in where your pinky is located, even though you're hopefully not moving your arm, waving it left and right. If you stretch out your arm and you blink left and right, you should notice that there's still a shift, but is much, much smaller. So based on how much these stars are shifting left and right, we can figure out the distance that that star is from Earth, if we know the distance that Earth is from the sun. The third step, which Hubble used, Hubble kind of just assumed that, or not just Hubble, but other astronomers at that era assumed that galaxies all had the same brightness, intrinsic brightness. And the galaxies that looked fainter were farther away than the galaxies that looked brighter. And that's partially correct. It's true that Andromeda is one of the brighter galaxies in our sky. It's one of the only galaxies in the northern hemisphere that we can see with the naked eye. But it turns out that galaxies have billions of change in luminosity, like the figure I showed you a while ago. But nevertheless, for stars, if we can find a star where we know exactly how bright it is, which is the luminosity, and we measure its brightness, then we can work out what the distance should be. And as far as these stars, in terms of measuring large distances out to galaxies, do you all think it'd be more useful to use high luminosity stars or low luminosity stars? High luminosity stars, bigger the better. Almost like Texas in here. All right, so we want high luminosity stars, and it turns out that for the stars, so this is a HR diagram, as mentioned before, we have luminosity, temperature. It turns out that stars along this instability strip, so-called, tend to fluctuate in their brightness in a very regular pattern, where we've been able to work out if we can look at the period of their increase, decrease in brightness, then we automatically know what their luminosity is based on stars that we actually can measure the parallax to. And these were originally Cepheid stars. Now, Hubble used Cepheid stars originally, and it turned out that he found that the universe was supposed to be around 1 billion years old, whereas geologists at the time already knew that the Earth was 4.5 billion years old. This was a huge embarrassment, but he still published. It was pretty courageous, I think, that he just said, this is the data, I'm not going to interpret it. And he let other people worry about it. Now, what it turned out, what really saved Hubble's law and this idea of a Big Bang theory were stars that are not actually Cepheids, but are lower luminosity. We can't use them for many galaxies. They're called RR Lyrae stars. These are actually main sequence stars. So they're a lot smaller, lower luminosity than the Cepheids. But because there are a lot more stars along the so-called main sequence than there are of the giant stars, they were able to work out the uncertainty in the brightness much more rigorously for the RR Lyrae stars. All right, so we can use Cepheid stars, and this is how Hubble showed that Andromeda had to be around 1 million light years away. Now we know that's much farther. It's more like 2 million light years away. We had some idea that it was far away. And then when we go kind of beyond Cepheids, which we know have this nice period luminosity relationship, we can also use white dwarf supernovae, where this is looking at a galaxy, and we have a specific type of supernovae, where these are not standard candles. Maybe you've been told that they are standard candles, but these white dwarf supernovae are so-called standardizable candles. And that is because based on their spectra and based on their peak brightness, we can match and stack them, and we can scale them up and make them into standard candles and figure out just how far away these extremely distant galaxies are. And Adam Rees, Saul Perlmutter, and a couple of other folks won the 2011 Nobel Prize looking at white dwarf supernovae and looking at how Hubble's law depended for the most distant galaxies and showed that there was an increase in the expansion rate. So we now think that there's some mysterious dark energy which is fueling this expansion, which I otherwise won't really talk about in this little talk. Now, if we go to and look at some of these galaxies and we compare kind of before there was a supernova that went off and afterwards, the kind of incredible thing is just how bright these supernovae are relative to the host galaxy. We have just a single star that is in at least order of magnitudes within the brightness of the entire galaxy. So we can look out to 10 billion light years or so with this method, out to some of the most distant galaxies. All right, and then we already talked about this a little bit for Hubble looking out beyond the Milky Way, but I'm not sure if everyone has seen this image of Hubble at the telescope before. It's one of my favorite images of Hubble. And so I'm gonna kind of gloss over some of these slides and just kind of jump us to the fact that Hubble was able to settle that great debate in the 1920s. Henrietta Leavitt was one of the astronomers that came up with that period luminosity relationship for the Cepheids that Hubble used. It turns out that the Swedish committee that chooses the Nobel Prize winners was going to choose Henrietta Leavitt, but you can't give a Nobel Prize to someone that's passed away. And she had passed away a couple years before Hubble had ended up making this discovery, which is too bad because she would have been the first astronomer to win a Nobel Prize if they had given it to her, and also the first woman to have won a Nobel Prize for that matter. Okay. Maybe just first woman astronomer then, or yeah, because I think Marie Curie was 1911 or so, 19, what? 19, early 1900s. Yeah, this would have been 1930 or so. I think that does predate Marie Curie. All right, and then we roughly covered everything. So this is actually an image. If you look at Hubble's original paper, these are different galaxies that are plotted, and it's kind of fun that he drew this, by hand. Didn't have computers to do everything. So we have the velocity on the y-axis, the distance on the x-axis in 2 million parsecs. And there's a pretty nice linear relationship here. Now, where this velocity is coming from, okay, so where this velocity is coming from is looking at the spectra of these galaxies. You notice that there is a redshift in most of the spectrum. Andromeda is blue shifted. So Andromeda appears to be moving towards the Milky Way. But most of the distant galaxies, there is a shift. And if you line up the different peaks in the spectra compared to what we know about where the spectrum is for nearby galaxies, he's able to come up with this redshift and convert that into a velocity, since they knew about the speed of light at that time. And we get this nice linear relationship, which is Hubble's law, which says that the farther a galaxy is from us, the faster it is flying away from us, almost in terror, it sounds like. And I'm sure that you all know about what Hubble's law means for the origins of the universe. So this is a rough overview of what I covered in a class last semester. I think that there should have been some new tidbits, probably a lot of stuff that you already know a lot about. So I'm gonna end it there. Are there any questions that people have? Yeah.
So how do you say these Cephid, how do you say it?
I call them Cepheids. I'm not sure if Delta Cephi. There is the Delta Cephi in the Cepheus constellation. I still might be pronouncing that incorrectly.
But how do you find one of the variables in these distant galaxies?
Yeah, good question. So for these galaxies, you are basically looking at the changes in brightness over time. So you have to be able to resolve the individual stars.
Okay.
For the most distant galaxies, we cannot use the Cepheid relationship anymore. So what Hubble did was use the redshift, and then after tuning Hubble's law for relatively nearby galaxies, like Andromeda, for example. Andromeda doesn't really work for Hubble's law specifically, but some close enough by that we have Cepheids that work, but is still distant enough that there is a redshift of the light. If you can calibrate Hubble's law based on galaxies that do have Cepheids, then for the most distant galaxies, you can figure out their distance by Hubble's law. The other way is using the white dwarf supernovae. But so we can't use Cepheids for galaxies out to billions of years or billions of light years from us. Mike?
I was gonna comment that,
Sure.
a guy named, I think it was Walter Bradley, in the fifties,
Hmm.
made the discovery that there are two types of Cepheids.
Mm-hmm.
And the Cepheids that, Hubble looked at were the brighter ones, they didn't really have enough, but in her studies, her computations were done on the dimmer ones. And so for that reason, Hubble grossly underestimated the distances that Andromeda.
Mm-hmm.
And so Roddy and others had to re-compute all the distances later on. And found out that they were grossly underestimated that original Hubble. No fault to Hubble, nobody.
Sure.
Time, but
Yep.
the other comment I was gonna make, there is a fellow that most people probably haven't heard of. Just Melvin Slifer, Ian Slifer.
Yeah.
Yep.
He's from Indiana. believe it or not.
Oh, okay.
From a little town called Mulberry, Indiana, which is close to Purdue. And he graduated from IU and got his PhD from IU. He was the first one that really recognized using spectroscopy that Andromeda, to its blue shifting and other more distinct nebula, as they call them, really call them, they were repeated.
Yes.
And he made a presentation that Hubble was having right before Hubble started his meeting. He was a real pioneer.
Yeah, so Slifer was one of the first to notice the redshift of distant galaxies. And then also another important astronomer of the time, Shapley, who was part of the great debate, actually. He was arguing for the nebulae being external galaxies. Shapley also observed redshifts of these galaxies, but it was really put the pieces together and really came up with a broader explanation for these things. Hands and then hand.
This is not what you covered, but I got a question that approached me.
Sure.
Do all galaxies have rotation? And if they have rotation, can they rotate both ways, or is the laws of physics, or we don't know?
Okay, yeah, fun question. So for spiral galaxies, we do seem to notice that there is a relative blue shift and red shift if you're able to look at the spectra of individual stars or just parts of that galaxy, which suggests that there is some rotation. And we notice that rotation happening both in a clockwise fashion with respect to us and a counterclockwise fashion with respect to us. For elliptical galaxies, it's been long debated whether there's any rotation in them or not. It's a lot harder because their stars are farther distributed, but it does still seem like there is overall some net rotation, but still debated about whether this falls under a 2-axis sort of system or a 3-axis rotation, which personally I have a hard time envisioning a 3-axis rotation. And then hands.
Picture, this, I know it's from soft, but
Sure.
the current
about the Cepheid Valley.
Yeah.
And I was wondering, are there just particular, they show up in a particular type of galaxy? You've seen more, you've got Mixed, you've got, spirals
Yeah.
and water spirals. Do the Cepheid variables fall into a particular class of galaxy?
Yeah, good question. So the Cepheid stars are giant stars. They do
Yeah,
not
they-
fall along the main sequence, and therefore the galaxies do not hold on to their Cepheids for a very long time. If you're going to have Cepheids that last there for a long enough time for us to observe them, then there needs to be relatively active star formation. So we don't expect to see Cepheids in elliptical galaxies. We more expect to see Cepheids in spiral galaxies. There are some other methods that we can use in elliptical galaxies. There's the so-called fundamental plane relationship between the spheroidal velocity of the stars orbiting an elliptical galaxy with the radius of the elliptical galaxy, which for some elliptical galaxies, they can happen to have some Cepheids just after their star formation has turned off or so. And we've been able to correlate the Cepheid relationship to this fundamental plane relationship, but we typically have to use different methods. The other thing about elliptical galaxies, because they have older stellar populations, so the giant stars, after they, especially for the low mass stars, the giant stars end their lives as planetary nebulae, and they leave a white dwarf behind. So the elliptical galaxies are more likely to have those white dwarf supernovae than the spiral galaxies. So there's a bit of a trade-off there. Any other questions? Yep.
So you've been following the controversy on these galaxies they keep finding closer and closer to the Big Bang
Yes.
with the web and how they don't.
Supposedly.
Yeah, do you want to talk about that at all?
I will talk about it, but you should take everything with a grain of salt. The main thing that I will be doing is rubbing my grain of salt into those results, which is that so far, so back in 2022, after the first release of the James Webb data, there are these claims that there are massive galaxies that seem to have formed within a few hundred millions of years after the Big Bang. And that is way too quick for any of our models of galaxy formation to have formed them. And so back at my previous institution, the Max Planck Institute for Astrophysics, there were a lot of cosmologists there that got really excited, and they said this is evidence for warm dark matter. In other words, a form of dark matter that can collide with itself, that can annihilate, sort of like with matter and antimatter. And so that is one way that you can form galaxies much more rapidly than we were expecting, is with warm dark matter. However, those results were using photometry from James Webb Space Telescope, not spectroscopy, to get a really well-defined redshift. And what a couple of follow-up studies have found so far is that those galaxies that seemed like they formed just a few hundred million years after the Big Bang are still very relatively old, redshift of 9, so they formed maybe a couple 100 million years, or maybe more like 800-900 million years after the Big Bang. But they're not a problem to current models for galaxy formation. The reason why they looked so red photometrically is because those galaxies were much dustier than average. But it makes sense that James Webb is able to see these dusty galaxies that Hubble could not see, because we're looking in the infrared now. So anytime that shows up, an astronomer shows up that you want to ask that question to, you can ask it. The other thing you can ask is, do we have spectroscopic confirmation of those really massive galaxies? The answer to my mind at this point is still no.
Cause YouTube's just full of those.
Yeah.
Those,
About what does it mean?
Yeah.
Yeah. But I personally don't trust it yet. All right, so I think I'm gonna end this now. If you have any additional questions for me, I can hang out for a couple of minutes. Oops.
How about a round of applause?
I know we'd all like to have you back again.
I appreciate your attention and your participation. Apologies to all of those that I picked on. Congrats to those that I did not quite pick on, but next time I might get you. So you never know.
Thank you.
All right.
I have a couple, I can talk to you privately.
Either way, sure.
One of the major goals for our observatory that we had as a vision was that we could begin some collaboration with students in
Okay.
astronomy.
Mm-hmm.
We had one professor from here. They had just built the observatory here on campus.
Mm-hmm.
Well, they're out listening to that. And of course, it's different than ours. But he said, I mentioned this collaboration. He said, oh, well, you wouldn't have to have spectrograph, would you? And I said, no, look, we can get one.
Okay.
Now we have one.
Okay.
And we have some people that have been working with it and interested in working with the student. And also, we would love to do anything else that a student would need, like you mentioned, imaging, and that sort of thing.
Mm-hmm.
Yeah, we have members who would be interested in working with him.
Okay.
So, Farber Cheney, observatory director, and when we have a project within our society, it's called the Star Quest Project.
Okay.
And it is established as a way of creating task teams to perform certain tasks
Mm-hmm.
and give support in certain areas. And you can apply it to academic studies also. As well, that's what we use to build an observatory. And then to correct and deal with some of the ways we approach the public and things that we can do. And we use the project to look ahead in like in a 5-year program to see where we can improve things. We would love to get into a program that has a goal for us to meet in collaborating with you all. So that, I just want you to know that exists within society as a tool to help.
Yeah, very, very nice to know. As far as the observatory, do you know the limiting magnitude for the telescope and camera?
Well,
Yeah. It depends also on the light pollution.
For the spectrograph.
Not as much for the spectrograph, unfortunately. I mean, the spectrograph, you can do a lot of great things, so it's great that you have a
16-inch
spectrograph.
scope.
16-inch, pretty good,
So,
but it also depends on the amount of light pollution, so I don't know where you're located.
Well, in the winter, deep in the winter, we can see Yeah, no way.
Oh, okay,
It's about a border 3-4 looking east and about a border 5 or so looking west. It's where we build.
We are,
okay,
we are also aware that we live in the Great Lakes region. The number of clear observing nights, in the months of February and March, is like big and cool. And so that's why we closed the observatory to the public from December through March.
mm-hmm,
And we closed them after November and open again to the public. But it's, you know, like a night like tonight, hey, man, it's clear.
yeah, it seems like a pretty good
Millions of
tonight.
people out of the observatory. So, with that as a problem, we also have some, Neil can help you with that, where, we, of course, we don't need the observatory to do it either, but we'll at least go online and be a partner with observatories around the world.
Oh, okay,
But again, we have some people who are interested in that. Good work with that.
okay, yeah, sounds great. Thank you.
We're doing a lot of people are doing photography too. Getting
Okay.
students are ever interested in that. These cheap cameras now are so readily available. And, Sharp Cap is what several of us use. Are you familiar with that?
I haven't heard of SharpCat.
That's a, English guy developed the software that's really pretty easy to use with a camera, and you can stack with it.
Okay,
And of course, these newer e-scopes, they stack on their own, you know.
mm-hmm,
So if any students are interested in something like that,
okay,
quite a bit of that going on.
good to know.
Do a lot of public outreach on, April through November. Star parties and stuff.
Okay, are those monthly or so, or?
Depending on clear.
Yeah, okay.
Saturday night.
Clears, okay.
It's like an hour after
Any clear
sunset.
Saturday night.
Includes Saturday.
April through November.
Okay,
I sent you a copy of this, I believe, you got an email.
yes, I think I
So
got
if you
that,
look
yes.
in there, we'll start listing upcoming star parties too. And we do the public deep sky, or the public viewing will start.
Okay,
So you can bring your students out if you want.
yeah, that'd be great.
Yeah, we can schedule something for you.
Yeah, we have class through May, so we'll have a couple weeks in April potentially.
We
See if-
did these solar eclipse in April.
Yeah.
April the 8th.
Mm-hmm. Yeah, where are you all going? Is there anywhere in particular you all
Our
are?
observatory's in New Haven.
Okay,
Yeah, we had to move from Fort Wayne, we moved out to New Haven for better sky, and
okay.
they didn't like to see more, they wanted to.
But for the eclipse, I don't think that New Haven will have totality either, right?
97%.
Oh, you will have some. Oh, okay. Hmm.
Just barely. Just right on the 47.
Yeah, we don't hear at all. I don't
No.
think.
We're
Okay,
gonna have at the observatories like 47 seconds.
well, that's,
Totality.
I mean, that's still a lot better than certain places, so. Yeah. Okay, great, cool, thank you.